and welcome to another episode of Twiml Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. The show you're about to hear is part 2 of our O'Reilly AI New York series, sponsored by Intel Nervana. I'm super grateful to them for helping make this series possible, and I'm excited about the cool stuff they launched at the O'Reilly AI New York conference, including version 2.0 of their Neon framework and their new Nervana Graph project. Be sure to check them out at intelnervana.com. If you haven't already listened to the first show in this series, where I interview Naveen Rao, who leads Intel's newly formed AI products group, and Hanlin Tang, an algorithms engineer on that team, it's Twiml Talk number 31, and you definitely want to start there. My guest for this show is Doug Eck of Google Brain. Doug did a keynote at the O'Reilly conference on Magenta, Google's project for melding machine learning and the arts. Doug and I talk about the newly announced Performance RNN project, which uses neural networks to create expressive AI-generated music. The demonstrations of this project are truly incredible, and I encourage you to check them out via the links we're placing in the show notes. All right, on to the show. All right, hey everyone, I am here with Doug Eck at the O'Reilly AI conference. Doug is a research scientist on the Google Brain team who's principally focused on the Magenta project. Doug, welcome to the podcast.
Hey Sam, thanks for having me. Excited to be here.
Absolutely. So this podcast, while I focus on interviews now, I originally focused on covering news in the space, and I covered the Magenta project when it launched. And I remember this vividly because my daughter was in a summer program or leadership program or something. I live in St. Louis, and I had to drive her downstate, and I spent a bunch of time on the trip back listening to something about, I might have been listening to my notes or articles that I had doing text to voice about the Magenta project. And so I'm excited to finally get a chance to talk to you about it and learn more about it. And yeah. So welcome once again.
I'm happy to be here a little over a year later from our initial launch and still at it.
Absolutely. And I think this is the first time from an interview perspective that we're really getting into the intersection of AI and art, which is an area that I've been wanting to talk a little bit more about as well. So very excited to have you on. Earlier today, you delivered a keynote at the conference, and we'll jump into that. But first, why don't you walk us through your background and how you got into AI?
So how did I get into AI? Good question. My undergraduate was in English literature, creative writing, and I finished that. And it turns out, some of your listeners may not know this, but it's hard to get a job when your undergraduate's in English literature. You actually have to work at something. So, there's David Foster Wallace, and then there's me. I became a database programmer, which actually I love coding, and worked for a while as just a coder, coding databases in Albuquerque, New Mexico, and playing music. The pinnacle of my music career happened in Albuquerque as well, playing for dozens of fans in coffee houses all around the street.
Is there a nice scene there?
I don't know. I just was doing what I could. Was passionate about it. And I drifted back into grad school. I think I was just, for the intellectual challenge of it, and it made more sense to stay with computer science. So actually, I think it was one of the better decisions that I made in my life. I just naively took the joint, the overlap of two things I was passionate about, which was computing and music. And I just said, well, I like music and I like computers, so what can you do with computers and music? And, I was 24, and that was what I was thinking. And I said, hey, let's do AI. Let's do AI and music. So I wanted to work with a guy named Doug Hofstetter at Indiana University.
Okay.
I ended up actually not doing my PhD under his direction, but took courses with him and ended up working with some other advisors there. Just kind of dove into a PhD in music and music cognition and computer science.
Wow.
And kind of kept at it. And eventually ended up at Google, having been a faculty member for a while at University of Montreal.
Okay.
But really it was kind of following a passion, just doing what I thought I was good at.
Oh, that's awesome. So maybe tell us a little bit about your keynote today, and along the way weave in Magenta, or you can start with Magenta and then go into the keynote, whatever kind of makes the most sense.
Sure. Today's keynote had a particular focus that I think is important, which is that we can't do machine learning for music or art without the music and the art. So, machine learning is about learning how to solve a problem. You build an algorithm that itself can learn how to solve a problem. So I guess it stands to reason that if you want to build machine learning algorithms that can make music or make art or be tools for musicians and tools for artists, they have to see the right data. They have to see the world in the right way. And so I talked about 2 projects. One of them came out today on the Magenta blog. Please check it out, g.co/Magenta. It's a recurrent neural network trained to make piano music perform a score that it writes. And crucially, it's trained on real piano performances captured in MIDI. And the captured in MIDI really isn't that important. We still know where all of the keys were pressed and how long they were pressed and how how hard the velocity, etc. For your listeners who aren't familiar with MIDI, think of that as just kind of a way to store the events that happen when you play a synthesizer or electric keyboard or an appropriate piano. And it turns out that when you train on this data versus a bunch of musical scores, that is with no performance, timing, just the score, the resulting output of the models is dramatically different. And to my ear, at least, much more human sounding, almost delicate sometimes in terms of how the model figures out how to play the piano. So I thought that was a really nice story.
The scores that you played during the keynote were incredible. I mean, the after, like there was the before and the after. The before is just the model trained on the score, but the after was incorporating in, I guess, the more subtle effects like, I don't know, attack and delay, I guess are the ways I'm thinking of it, but like just the force with which they press the notes and that kind of thing.
Yeah,
and
that's it.
Timing, subtle timing differences. And I never heard anything like that from a computer-generated program.
Yeah, it's quite nice. I mean, I haven't done a thorough enough literature search to know if, I haven't heard anything like it either. I mean, hopefully people will come up and say, hey, we did this cool work before, and we'll say, great, we'll credit it, we'll learn from it. This is a research project, we're trying to always give credit where it's due, but I haven't heard anything quite like this. And I think you're right. The way to think about it is, Chopin wrote a piece of music, right? Yet we still love listening to different pianists interpret that music.
Right.
And especially with that kind of music, the interpretation actually matters. If you don't believe it, it's really entertaining to listen to a truly robotic performance of a piece of music. It just doesn't work.
Right.
And I think, in modern pop and rock and jazz, it's even more so the case. Like, think of Jimi Hendrix playing the Star Spangled Banner. Like, we're not listening to that because of the score, right? Because this melody is so good, right? It has cultural significance, and it's this carrier for the sounds that Jimmy's making with his guitar. So, like, this idea that the expressive timing matters is, if you kind of unpeel the onion a little bit, is pretty clear. And it's really fun to see what a model can do when it finally has that data.
Well, you made a comment that I thought was really, really interesting, and that was that, what this work gets you closer to is looking at the keyboard or other instruments in other cases, but as, sensors that are capturing sensory motor control from humans all the way up, from fingers to muscles to, neural transmission and that kind of stuff. Can you elaborate on that a little bit?
Yeah. So first,
did I capture that correctly?
You did. I think you did. Yeah. So first, in terms of just the model, what's being captured is how hard the finger hit the key, and there are lots of just kind of the data picks up on human constraints that I think are important to music.
Right.
And I've always been fascinated by the connections between dance and music, and between motor control in general and music. There's lots, piles of books written about why is music here? Is it maybe creating co-presence between people, or it's about motor control synchronization? It's about just having fun. But in any case, it's clear that there's the motoric aspect is really important. Same thing is true for drawing, right? The constraints of the hand, what the hand can do, I think, is really important, whether it's holding a paintbrush, or a pencil. I guess arguably if you move to Photoshop, you're in a different world. I'm not sure that it matters how your hand holds the mouse, but maybe there too. And it's really cool that we're able to train on the data that drives that. I could say more about this if you want.
Sure,
okay,
absolutely.
So the other thing that I would add is a lot of people work in machine learning right now are working with images and with audio. Well, I mean, we are too, and I think it's really important. But I'm always but intrigued by the idea that when we as people, when we make new artifacts, whether it's like a new painting or a new piece of music, we tend to actually not do it pixel by pixel, or, we don't have the control, even our voices, we don't really have control over the waveform, right? We have a buzzer in our throat called vocal cords, and then we're shaping our vocal tract, right? It's very, very, in machine learning terms, it's a pretty low dimensional control surface, right? So we're not dealing with like millions of parameters. We're able to like move some muscles around and make something vibrate. With playing a piano, we build this thing out of wood and metal, and then fundamentally we bang it with our fingers, right? And so, I think trying to do machine learning for art and music, trying to move into these spaces that are really low dimensional. And by that I mean, you've only got 88 keys, and that may seem like a lot until you think of the number of pixels there are in an image, or the number of moving numbers there are in a 1 second of CD quality audio. It's a relatively low number of parameters to work with. And I think that ties to these really beautiful ideas about, what is meaning, but at some level compression, like just pulling the important bits out of a hard problem. And it's a little easier to get there. I'm getting too philosophical, but.
No, I mean, it's an interesting conversation, and it reminds me a little bit of, I'm not much of an audiophile, admittedly, or not at all an audiophile, really, admittedly. But,
pretty good headphones. I mean, come on.
Oh, well. But, you get people argue over, CDs versus vinyl records, and like they'll get into these debates about the richness of the vinyl records, or transistors versus tubes and that kind of thing. And it does, when you think about it in this context, it does kind of think of, the machine learning, the input that we're giving to machine learning models in a lot of ways is kind of reductionist. And how do we make sure we don't reduce out the essence of the thing, right? Does that make any sense?
Yeah, it does. I mean, so first, I think that we are always at risk of doing that. And what makes the problem retain for me its beauty is that, we're always there. Like, I'm not interested in a machine learning algorithm where I can just push a button and have it do its work. I mean, I think it's cool, like the samples we posted today, we're basically pushing a button, but that's more or less to understand how the model works. I think these get interesting when you close the loop and you have musicians able to work with them and use them as ways to kind of expand possibilities, or create some line and then you add another line, et cetera, like that. I think that becomes less reductionist.
Right.
But yeah, look, let's be real. What are these models doing? They're basically warping data. They're doing they're taking some numbers in and they're transforming them, and they're pushing some numbers out. Hopefully you've done the math right, and you can roll the dice and sample from these and get lots of different really interesting instances. But yeah, I mean, reductionist is a pretty fair term.
Are we close to being able to do like a music style transfer? Like, I've got this rough idea of, a score or melody, or, I don't know what the input would be, but, Chopinize this for me. The demo that you played was kind of evocative of that kind of idea for me.
If we rely on the representation of MIDI, where what we're manipulating are the notes and when they happen and how many of them there are, and we're adding and subtracting notes and we're performing them. Yeah, I think we can imagine with some work being able to do a style transfer over something. However, can we take an Adele tune and make it sound like it was done by, I mentioned Jimi Hendrix, right?
Right.
It's a very different kind of style transform. Or can we take an Adele tune and make it sound like bebop jazz from the audio?
Right.
We're very, very far from that. And I think, to be honest, I think that's more getting at the flavor of what style transfer for images does. And the reason I bring it up is that there's a nice trick in style transfer for images. For example, taking a painting and making it look more like Picasso, which is that it's looking at little patches in the image, and the patches are varying sizes, but it's always local, right? Literally, you can imagine just like moving a little spotlight over the image. And then doing transforms at some layer of granularity. So you can like get thicker brush strokes versus thinner ones, right? But in music, music unfolds in time, and it's not always the case that it's the nearest sounds that are the most important. There's not this locality, this spatial locality in music. And I think that would make like a style transfer so that something sounded more like, an electric guitar quite a bit harder. Certainly the tools that are used for image style transfer don't quite make sense, which is why, by the way, we don't see, lots of groups have tried this. We don't see compelling audio-based style transfers.
Okay.
We're getting there. We'll get there. I mean, someone will figure it out, but it's just, it doesn't sort of fall out for free from the image side.
Right. So Why don't you walk us through the kind of the technical underpinnings, the architecture of the project that we just talked about?
The project Performance RNN, we give things names just to have something to talk about. It's not an important name, but Performance RNN is a recurrent neural network called LSTM, long short-term memory, that is listening to lots and lots of performances, in this case piano performances. What it's seeing is actually a very simple encoding of that performance. A note turned on, it had this velocity. A note turned off, let's advance time, let's advance the clock. So it's almost like, imagine you've got a paper punch and you're cutting holes. You punch, 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 and then you move forward and you punch, punch, punch. It's a very, very, very simple way to represent the data. But it's not losing any of the data. You can reconstruct the entire performance from there. Right? The recurrent neural network is trying to solve an interesting problem. It's listening, so to speak. It's processing this information. It's trying to predict what's coming next. And in our case, it can predict, hey, generate another note, turn off a note, or move the clock. And every time it gets it right, every time it predicts correctly what it's being trained on, it gets a good job. And every time it gets it wrong, then we adjust the weights of the network. So these are weighted connections between computational units or nodes in the network, so that it does better next time. And so it's really playing kind of a funny telephone game, where maybe that's not the right word for it. I had an analogy for this, but it's kind of a weird thought. You're listening, you've heard 6 notes of a melody, and you're trying to guess what the 7th note is. Even people aren't going to get it right all the time, because there's lots of possible ways in which things can go. So in the end, these models, they don't memorize specific tunes. Instead, they kind of figure out patterns of what should come next given these previous notes. And in fact, they learn about chords, they learn about arpeggiation, they learn about scales, because those happen in the data. And when we want to make a piece of music, we do take a clever, very simple trick that's been around for 20 years. You start with a note or two, and then you predict what should come next. And that's like it's not an exact answer. The model says these are the possible things that could come next. You choose one based upon those probabilities, and then you feed it in. You feed the network's output back in as input, and you kind of keep going, called auto-regression. And in that way, you end up composing a new score.
Okay. How many order of magnitude musical samples are you training this on? And are you training them on full scores or snippets, or does that matter?
It does matter. In the end, for technical reasons, you end up kind of chunking things, but we have ways to do that automatically. So in terms of when the model receives the input, it processes an entire score. I think it's on the order of 20 or 30,000 pieces of music in this case. It's not huge. They're all performances, and they're all from solo piano.
Okay.
So, and
did you commission them or collect
no, these
them?
So these are all pieces that were, like Chopin, it's all public old classical music, and they're performances that come from a number of sources, all kind of freely out there on the web. And you can track those down if you follow the Magenta blog, where we have it's probably not interesting to go into where the data sources actually come from, but but behind it all are people having performed these sometimes for competitions. One of the sources that you can use is Yamaha has a particular kind of piano that's like a player piano called the disclavier, and they've had competitions where very top tier pianists come and play, and at the same time the piano records all of the movements of the hammers, so you have the trace left behind of what they played.
Oh wow!
So we can train on data like that.
Okay. Oh, really interesting. So you've got this 20, 30,000, and were they all specifically Chopin, or
no, not at
how
all.
much variation do you have?
Large variation across the classical tradition. And we can collect other data sets. In fact, it's perfectly reasonable for someone to actually just collect a few hours of playing of their own, and that's going to be enough to train a model. Not 1 hour, but if one of your listeners is, say, like a jazz pianist and does jazz improv, you could train a model on just a few hours of improv, and then they'd have their own. Like the model would encode their own playing style, which is kind of cool, right? And then when you sample from the model, you can kind of hear some of your own aspects of playing.
Wow. To what degree was the network architecture for this particular neural network, how is it unique from other network architectures that are used for, other LSTM-based network architectures that are used for the kind of thing you do to, we've seen the projects where we're getting scripts auto-generated.
Right, Ross Goodwin, yeah. Shout out to Ross.
Yeah.
The network is actually pretty much a generic LSTM. What's somewhat novel is the representation of the data, so what the model's trying to predict. There have been other people who have predicted like the duration of a note in terms of its relative duration in the score. Like I'm going to generate a middle C and it's going to be a 16th note. And we've simply extended that to say, well, forget about whether it's a 16th note. Instead, let's just move the clock forward some number of milliseconds, and that way we'll just learn about real time.
Right.
So if that's not clear, that means we don't need a metronome to figure out what a quarter note is, right? If that's not clear, like what a quarter note is that it's the quarter of a measure, and what a measure is defined by the beat. And if the beat's fast, a quarter note takes less time to be played, right? Here we're just saying, we're just going to look at the time of the piece as it unfolds in the performance. And so the model doesn't know what a quarter note is at all. It just generates notes and moves the clock. And that I think that's unique. Again, we just put this blog posting out and we're in the middle of writing a paper around it. And it's pretty hard in research to do something that's completely new. You always find that someone did something similar, right? I mean, there's almost nothing new under the stars and sun. But
nice. Well, we'll definitely include the audio that you shared in your keynote in the show notes for folks to check out. It was really, really compelling. You also talked about a project based on the Google Draw experiment. Yeah. Tell us a little bit about that one.
That was an AI experiment called QuickDraw. It was done by the Creative Lab folks in New York at Google. And what they did was we already had some image classifiers that we can use that can identify like, tens of thousands of different kinds of images. You see, you point your mobile device and it recognizes through the camera that that's a lamp or that's a dog or that's, a cell phone. And so someone had a clever idea of saying, well, could it identify a sketch of a dog or a sketch of a cell phone? It turns out, it can. So you get to play Pictionary against an image classifier. Actually, you're playing Pictionary with an image classifier. Remember, Pictionary is collaborative, right? And so, you're given a prompt like, hey, you have 20 seconds to draw a dog. And you try to draw a dog. And if the image classifier can guess it, then you get a point, right? So at some point, we decided we wanted to use this data for machine learning. So we changed the messaging on the site. So it said, hey, if you want to play the game, we're just going to keep anonymized drawings around. We're going to learn from them, right? We're going to train. So we kept that data. We gave it back to the community to use for artistic purposes. And people have done tons of crazy things with this data.
What are some of those things?
Oh, so this, by the way, this isn't our machine learning. This is just the people's drawings. Analyzing how different people in different cultures draw circles. Turns out, like, some cultures draw circles clockwise and other cultures draw them counterclockwise, and you kind of cluster things. The way that people draw chairs, Asian cultures apparently draw chairs often. I'm going to get these backwards because, they usually draw chairs
like from the legs up or something.
No, it's in three. Whether you do it in 3D or 2D. Whether a chair is just like an H almost, right? Which is what I would draw. And I think that's actually an Asian pattern. Or whether you actually draw it kind of in 3D. Yeah, someone else outside of Google took the data, the circle stuff. It's like a blog posting from a couple weeks ago. I encourage your listeners to find it. Just Google like QuickDraw circles. And it has you draw a circle and it tells you some things about the circle you drew and analyzes the circles from around the world. And so I don't know, you just kind of get this kind of fun. I mean, it's not world changing, but it's interesting, right? There's a kind of sociology behind it. Anyway, I digress. We had this data, and David Ha, who is the primary person on this paper, decided to train a recurrent neural network to try to reproduce the strokes. And we have the strokes as they appeared in order. So, if you were trying to draw a garden, if you drew a flower first and then you drew the grass, then it would be reproduced in that order. This was a slightly different model. This was two different recurrent neural networks and an intermediate representation, but maybe that's too far afield too. The upshot is, you can now generate new instances of like dogs or cats or, there are several hundred classes and kind of try to get a better understanding of what people are doing when they draw them and also have a way to explore the space.
So what exactly does that mean? You've got a kind of decoder-encoder setup where the decoder is learning how people are drawing these things, and you've got an encoder that is trying to given a thing that it's trying to create that thing, or
I think you reverse the terms. You reverse the terms. So one way to think about it is that the work that I described with the Performance RNN, you could think of as a decoder. It's not encoding into some different representation. It's basically just taking the score and trying to predict the next note. This model does something slightly different. It takes the strokes and tries to encode them into a vector, into a sequence of numbers. And then only from that sequence of numbers does it try to reproduce or decode the drawing. So it's getting these strokes in, it's pushing some information via a recurrent neural network into this kind of intermediate representation called our latent space, if you want the technical term. And then it's trying to then recreate the drawing by decoding it using another recurrent neural network. And the reason that we use this intermediate step of this latent space is that if we've constructed it correctly, we can do a really nice job of generating new samples with lots of variance for the same problem. I don't know.
Elaborate on that.
Yeah, I have no idea how technical they get. So, for example, we could take the drawing of a face that has like almost like a triangle, inverted triangle, a really pointy chin, right? We could run that through the encoder, and that would give us some vector. And then we might take another face that's a big round face with a big round nose, and run that through the encoder, and that'll give us another vector in this latent space, right? But now we have these two vectors. They're not very big, maybe a few dozen numbers or maybe 100 numbers, and we could just take the average of those two. And that should, if we've trained our model right, give us the face that is kind of somewhere, kind of between this triangular face and between this circular face, right?
If you do that enough, you get to like the meaning of a face, right? Is that the idea? At some level?
I mean, you capture, in a hand-wavy philosophical way, you get the Platonic face.
Right.
In a less ridiculous way, at the very least, you get like, what's happening is that latent space is encoding those aspects of the face that are the most important to remember if you want to be able to cover the variance of faces. And so, it's captured something really important, some of the really important aspects of faces. So in that latent space, as you move around that space and maybe you generate some random vector in that space, you should still be able to decode some kind of face, right? That's called variational model.
Okay.
So I don't know if that captures the gist of the tech. I think one of the take-home messages is the reasons why we're caring about having this embedding space, this latent space, is that we can use it as a way to give artists more control over a model like that. So, for example, you could draw a face,
right,
and encode it through the encoder, and then now you have this vector, and you could perturb that vector, you could move that vector around, you could use this as a starting point for some other work with the model. You could just email that vector to someone else and they could reproduce it. They could know what you think about. Now, granted, this is all in the context of drawings that took 20 seconds to make using a mouse on a computer. So our expectations are not that, people will go, oh, I can make, the next Chagall painting or whatever with this. But that in principle, you have this space where, we can encode some drawing into some space that is kind of really good at storing drawings. And then from there, we can carry that around and we can decode not just that original drawing, but tons of drawings like it. And then maybe, be able to move forward with, possibilities for moving around that space for reasons like for animation and things like that.
Okay. It's interesting. One of the interviews I did yesterday that'll be coming out at the same time in this O'Reilly series was talking about Word2Vec. And it's interesting to kind of think about all of the various. We talked about several applications of embeddings in the context of Word2Vec and related things, but here's
this is definitely drawing to Vec.
Right.
Yeah.
Right. Yeah. So you encode your samples into this vector or a vector space, and then you can use that as almost like a filter for creating things through the decoding process. And I think one of the examples you showed was, and contextualize this for us, but you had folks draw like an 8-legged pig. You encoded that and then decoded it using the kind of the pig vector.
Yeah,
is that the right way to think about that?
Yeah. So you're training this autoencoder model only on pigs.
Yep.
So it knows nothing but pigs.
Yeah.
It's pigs all the way down. Right.
Yep.
And, we make these latent spaces pretty small and inject some noise. We don't want them to overfit. It's boring if they just memorize the data. Just use the data, right? So this little vector can barely manage to generate a pig, but it does a pretty good job of generating pigs. Yeah, and you give it a pig with 8 legs. Well, it never sees pigs with 8 legs. So it encodes, through the encoder, the recurrent neural network, it encodes some numbers that were driven by those strokes, including the 8 legs.
Mm-hmm.
But when it decodes it, what's remembered by that embedding is that there were 4, right? And I think it's kind of nice. Also the other example that I talked about in the keynote was if you have the same pig class, the same pig autoencoder, and you take a nice drawing of a semi-truck,
right?
It decodes, guess what, as a pig truck, right? Like it kind of turns into a pig because that's what the pig model knows about is pigs. And it's at one level, that's a weakness, right? It's like, well, but there are so many other things in the world. But of course, you can train more models, and you can train models that are conditional so they can represent more than one thing. It's that this latent space is really capturing some important aspects of pigness, right?
Mm-hmm.
And people someone else in open source, not us, took those very embeddings and then did something fun. They started looking for examples of pigs in the QuickDraw dataset that were far away from that embedding. So you imagine you embed a bunch of pigs, so you get the average embedding. You don't have to embed all of them, embed 10,000 of them, you get the average, right? Just take the average. And then from there you embed a pig and you take its distance. How far away is it from that average, right? And then what's fun is they just found really poorly drawn pigs, or occasionally someone had just written the word pig.
Okay.
And it's like, that's not a pig. I mean, it says pig, but these models didn't learn to read. And so you get this weird kind of fun outlier detection. And you can cluster this space too. That's often done with word devec models where you say, okay, like for cats, it's not that there are just, several million completely unique cats. People kind of either draw them in profile, or they draw the cat's head. Right. And sometimes the profile flips this way or this way. And if you, in this embedding space, if you do clustering in the embedding space, so you look for, it's not like given the number of the possible values in this embedding, everything is equally spread out. It's like there are mountains, right? And here's the profile mountain, and here's the profile the other way mountain, and here's the face mountain. And you can visualize that and kind of get an idea, what people are really doing with these drawings.
Can you then identify a distance from your average pig vector beyond which you won't be able to recognize something as a pig?
Yeah, and that's the classifier's job. In this case, it was an autoencoder, so it wasn't trying to decide whether something was a pig or not. It was trying to draw a pig. So there's no magic value, but you could always calculate one, right? You can kind of figure out where you're going. It's important to keep track of the goals, right? This is a kind of small. It's a large data set in terms of the number of samples we have, but it's a pretty simple drawing task. I think it's fun to think about where we can go if we have better data and better models.
And where's that?
So I think there are a couple of possibilities. One is that we just nail it, and we basically do something that happens 1 in a million times, which is we invent a new art form, or we enable a new art form. Now, it's been done before. Technology has done this before. The film camera enabled a new art form, right? The drum machine enabled a new art form. And we could probably, together, we could riff, and if we had a whiteboard, we'd come up with 30 or 40 of them. But we wouldn't want to forget that there were another, thousands and thousands of... Did the theremin invent a new art form? Maybe, right? The synthesizer, yes, right? So maybe we'll invent a new art form. And it's really interesting to think, what would... The core of that art form would be that the artist would have something smart against which to project ideas. I think that would be the core. That, you can try things out with your sequencer, or you can try things out with Photoshop, or you can try things out with a pen and paper. But the idea that we would have machine intelligence models trained that are, by analogy, as smart as Translate, right? Because they're trained right. And that's really, really interesting to me.
There's an inherent limitation in that we're training on, for the most part, things that we've seen before, right? And so it kind of cuts off, at least intuitively, seems to cut off this creative avenue for innovating, for, creating the wholly new thing.
I agree. And I think that if we create a new art form, it will be through many, many interaction loops of artists working with this technology. So that's not that crazy to think about if you watch what happened with the 808 drum machine and drum machines moving forward. People first used drum machines on sort of, Roland's terms. This is what a drum machine is,
Right.
But gradually they just were like, I'm going to use it however I want, right? And then the drum machines were manufactured to adapt to that, etc. And I think one way to think about this is, if this were to actually generate a new art form of interest, you train a model, it generates some things that are somewhat surprising to you, but you like. You keep them. You change your writing style somewhat, or you change your performance style somewhat. Maybe, like I can imagine living in a world where the data is so important, but like part of what you do as an artist is create data. And so in some sense, you are helping create this model because you're the one providing it with its lifeblood, with data. Or alternately, you're hacking the model, either because you're a coder, right?
Right.
So then you say, okay, this model changed slightly how I do music. Maybe it added some rhythms to my repertoire I don't usually use, or it does some crazy harmonization that I wouldn't normally do. And then you make some more music, and then you retrain your model, but now there's new stuff there, right? And you've moved a little bit, right? I don't think the movement has to be earthquake large. It doesn't have to be groundbreakingly large to be new, right? I mean, imagine just like if we kind of work out a new way to harmonize music. So you have a melody and you have all these extra voices. Just imagine via a model that's trained right, we suddenly get different kinds of harmonizations that we didn't get before. That would already be interesting. Or another example I like, which is crazy hard, but I think is very evocative. I think like something long form like a novel, right? And think about plot, right?
Right.
Like plot is hard, right? You can my hat's off to someone who can write like my hat's off to Game of Thrones and keeping all these characters straight, right? George R.R. Martin is my hero. But you could imagine like some writers care less about plot and they really care about character, they care about texture. Imagine the right kind of machine learning model that can generate intricate plots with really interesting relationships between characters and movement of action, right? Such that like maybe in a way that's even, at some level of complexity, too hard for a human to do because it can search out more possibilities. But yet maybe everything kind of clicks and lands and it feels good as the reader to be like, oh, wow, that character just came and did that. That's crazy, right? Almost like writing jokes that have sort of three punchlines that all land at the same time. That like, because, machine learning algorithms are really good at high dimensional spaces with lots of possibilities. Maybe we'd land at some new form of storytelling. I don't think it would be one where we would care about reading the computer's story, but that the computer might add something to the writer's world where like, in some sense, the writer might offload plot. Be like, I don't do plot. What I do with the plot is something even more interesting. Like I shape it, I craft it, I make it beautiful to read, right? So that's one way to think about it, that like, I don't want this to be too long-winded, but it's really important to me. Like what the drum machine did was, in one really important way, it offloaded some of the percussion work. But, if you want to be cynical about it, then you're like, oh yeah, and it just killed percussion. It didn't. It offloaded one thing, and that opened up a bunch of other opportunities, right? And so then the idea is, well, what sort of things can you offload onto a super smart machine learning model? And to be honest, I don't know. I don't know the answer. But I mean, if you move through different kinds of media, from painting to music to literature, you certainly can get some ideas.
Yeah. Awesome. And so Magenta as a whole is kind of an umbrella for a bunch of these different directions, right? Maybe take a second to talk about Magenta and how Google thinks about that, why Google's even, bothering. Tell us about Magenta.
Yeah, this is funny. This question usually comes early, right? It's good to have this come after people have heard some specifics. So the basic idea of Magenta is posing the question, what can we do with deep learning and reinforcement learning in the space of creativity? And we've already fully realized that the meat of the problem lies in these algorithms interacting with musicians and artists. And that's not because we're afraid of trying to get these models to be interesting on their own, but that I think that's how art works. It's collaborative. Other artists are working together, and we're thinking, these things are going to work with artists. And so in the last year, Magenta's been around publicly for about a year, and before we launched, we were working on it for another 6 months. We've done work in music sequence generation, including musical scores and also performances like we did today. We've done work in generating new kinds of sounds, the NSynth project, which is basically building a synthesizer where all of the sounds are dreamt up by a neural network. And we've done some unpublished work in joke telling. And
really?
It's unpublished because, well, it wasn't very funny. No, we did a summer internship, like looking at joke telling as an exercise in generating interesting surprises. I think especially punchline-driven humor is like, oh, that was surprising in a nice way. you know,
if you ask my kids, like getting to the level of dad joke, it should not be hard.
I know. We're both dads here. We should be experts at this. Like if we just team up. And what my motivation, actually speaking of kids, so let me finish. And then thinking a little bit more about language, but most of what we've had to do, and then learning to sketch RNN stuff, and then some implementations of style transfer for images. So we've got kind of a wide array of things that we're trying. I think the glue of the project, what holds it together, is we're limiting ourselves to deep learning and reinforcement learning. We're looking at creative applications of machine learning, but we're not going to try everything. Like there are lots of ways to solve these problems, lots of great ways.
Right.
We're not saying that machine learning is the only way of the sort we're doing. It's just like we got to limit ourselves to something. So we're really linked to TensorFlow. Also, that really what we care about are like behind this 1 year of trying some new things. I think the really core issues lift above any specific medium. I think it's about storytelling and narrative, whether it's music or paintings or literature, and it's about structure and narrative arc, and about these ideas about surprise and what makes something simple. So I think there's a whole area of like, you know, generative models for media that you know, can we generate interesting bits of media for us to share that help us tell the story of our lives, and you know, different modes of communication possibly coming from this, actually almost certainly coming from this. You know, those are the goals. Why is Google doing this? Well, like one thing is we're publishing a lot of papers, so we're part of Google Brain, and the framework of generative models is important. It's important. It's an important research topic, and the idea that you know, maybe you'd want to generate, you know, new candidate molecules. Maybe you'd want to look at healthcare. Maybe you'd want to look at something for robotics and generating trajectories. But I think, you know, when I look at what my kids are doing with their mobile devices, I've got a 13-year-old and an 18-year-old. You know, they're information seeking, they're entertainment, and they're communicating with their friends, right? So there's a huge chunk of what we're doing with computation that has to do with entertainment. And I think, you know, it's a really important area of research. I mean, just point blank, I think music and art are important. They are important for our lives, and it's absolutely worth investing some time into it.
Awesome.
So that's what we're doing.
Awesome. Anything else that you'd like to mention, or any other places that folks should look, or are there, you know, 3 canonical resources to, you know, for folks that really want to dig into this? Yeah.
So there's 2 things I would say. First, please visit g.co/Magenta. That's the shortest link I have. And we have a blog. We have a blog there that's getting. If you want to geek out, what'd you call it? Nerd time? What did you say?
Nerd alert.
Nerd. Yeah, we nerds, listener nerds. If you like that, come look at our blog. And the other thing is, we're very, very actively trying to engage with some particular types of folks in the community. There are 3 types. One type is pretty obvious: artists and musicians, fine. And then there's always the machine learning folks, nerd alert. But there's this middle ground where I think there's probably more there than any place else, and it's in this kind of world of creative coding. Do you know what I mean by that? So like,
well, tell me what you mean by that. I have my own ideas.
I mean, I'm sort of stealing that. You know, creative coding is just that. It's coding. I mean, the way I define it is, it's the creative aspects of coding, right? So I don't want to.
Creative aspects of coding, or coding applied to creative.
It's that. Yeah.
Aspects.
Sorry, I said it wrong. Yeah, and I think, you know, I was talking about how a musician might play a few hours of music and then use that to drive a machine learning model, and in some sense they're hacking the model because they're providing the data. But also building these models is a creative thing in and of itself. And we're trying to build some frameworks where, like, if there were an artist who knew how to code, you don't have to be like the world's best machine learning coder, but we have some models where, you know, you could change a few things. You could say, if you had some way that you could, for example, let's say you wanted the music that was generated by the model to be more shimmery, whatever that means, fine. If you think you know what it means, and you can define that in a way that if we get a piece of music and you say, oh, that sounds more shimmery, then we can actually use that. We can train the model to do a better job of generating that kind of music. Right. See what I'm saying? So I don't know. I think there's a whole direction of like having coding be part of artistic generation, and that machine learning and a project like Magenta is really a core place to try that. And so we're trying to get more people through open source to work with us, to collaborate with us, to make art and make music and hack stuff.
Awesome.
And so we'd love to see more people from your listeners join us. That's it. That's what I want to say.
Awesome. Well, thanks so much. I've really enjoyed this conversation, and I'm sure folks will enjoy listening to it.
Thanks for all of your great questions, Sam.
Thanks, Doug. All right, everyone, that is our show. Thanks so much for listening and for your continued support, comments, and feedback. A special thanks goes out to our series sponsor, Intel Nirvana. If you didn't catch the first show in this series, where I talked to Naveen Rao, the head of Intel's AI product group, about how they plan to leverage their leading position and proven history in silicon innovation to transform the world of AI, you're going to want to check that out next. For more information about Intel Nirvana's AI platform, visit intelnirvana.com. Remember that with this series, we've kicked off our giveaway for tickets to the AI conference. To enter, just let us know what you think about any of the podcasts in this series, or post your favorite quote from any of them on the show notes page, on Twitter, or via any of our social media channels. Make sure to mention at TWIML.ai, at Intel AI, and at the AI Conf so that we know you want to enter the contest. Full details can be found on the series page, and of course, all entrants get one of our slick TWIML laptop stickers. Speaking of the series page, you can find links to all of the individual show notes pages by visiting twimlai.com/O'ReillyAINY. Thanks so much for listening, and catch you next time.